This video is about designing multi-stage amplifiers at the block diagram level. It corresponds to section 18.3 of Applied Analog Electronics. Now, there's two main reasons why we go to multi-stage amplifiers. One of them is that we want to get a high frequency amplified, and the other one is that we have DC offsets that would cause us problems with the output range if we didn't deal with them. So let's look at both of these problems with a simplified example. Okay, let's say that our input signal, the thing that we want to amplify, is plus or minus 1 millivolt. That's the AC component, and there's going to be some DC bias. So V bias plus or minus 1 millivolt AC. But the amplifiers that we have available, the op-amp chimps or whatever they are, have an input offset somewhere in the range plus or minus 4 millivolts. Now the input offset is a DC bias, basically, that gets added to V bias. And it's not known. It's something that is guaranteed by the manufacturer to be in a certain range, but depending on manufacturing, depending on temperature, depending on all kinds of different things, the DC bias that you get in this input offset can differ. So we have to design taking that into account. Let's say also that this signal has information up to about 20 kilohertz. So we want to be able to amplify this signal to a large fraction of our analog to digital converter. And we can look at it and say, well, plus or minus a millivolt. Let's amplify this thing to be, Vref plus or minus a volt. So Vref is some voltage, center of our voltage range somewhere, and we want plus or minus 1 volt AC coming out of our amplifier. All right, how would we do this? Well, there's two things we have to do. We have to get rid of V bias, because that's not necessarily the same as Vref. And we have to amplify this from 1 millivolt to 1 volt. So this sounds like we could do this as a simple system where we would say, all right, we have, this is the input signal come in here, we'll have a high pass filter, and we'll have a gain of 1,000. All right, everything looks good. We have input signal coming in here, 1 millivolt plus or minus a millivolt, amplified by 1,000, going to plus or minus 1 volt. We have to figure out, well, what is the high pass filter here? How much DC are we getting rid of? That's how we're getting rid of the V bias. So it's going to have coming into it Vref, because we need to be recentering before we get to this amplifier. And this amplifier will also have to have Vref coming into it, so that it can be taking input from Vref, output at Vref, both relative to Vref. And so we will need to have some sort of block for generating Vref. All right. Do we have any problems here? Well, what sort of amplifier do we have here? Let's say that the amplifier chips we have available have a gain bandwidth product of 1 megahertz. Well, how much bandwidth are we going to have out of this amplifier if it's got a gain of 1,000? 1 megahertz divided by 1,000 means that our maximum gain, our maximum bandwidth is only 1 kilohertz. That's a problem, because we wanted 20 kilohertz. We also need to figure out how low a frequency is our signal interesting. Do we care about 1 hertz signals? Do we care about half hertz signals? Tenth of a hertz signals? That makes a difference, because this high pass filter, which is getting rid of the V bias, will also get rid of any really low frequencies. So we have to go back to our original specs and say, what were the ranges of the signal, not just the upper range, what was the lower range of those signals? So let's say we want this thing to amplify from 10 hertz to 20 kilohertz. Then we can set our high pass filter here to be at 10 hertz or anything lower. But we've got a problem here. Bandwidth of this one, we could get down to 10 hertz easily enough, but we can't get high enough frequencies through this thing. There's another problem here in that the signal that comes out of this high-pass filter will be centered at Vref. So it'll be Vref plus or minus 1 millivolt AC. But the amplifier itself is going to add a plus or minus 4 millivolts to that. And when we multiply that by 1,000, we've got a plus or minus 4 volt offset at the output. And that's not very good if our analog to digital converter was only going to be taking stuff with a little over 2 volt range. So, if we had that much extra range in the analog to digital converter, we would have asked for a bigger gain. So, we're running into trouble here. But there's things we can do about it. First of all, we can replace that 1000 gain with a two-stage amplifier. And we can make these two gains roughly equal. Now, 32 and 32 would be nice, making 1024, but it turns out 32 is a little bit difficult to get with standard resistors, but we can get a gain of 31 pretty easily, or 34. And so we can do either two stages, each of 31, and that would give us so 31 squared is 961. 31 times 34 is 1054. So depending whether we want a little bit high gain or a little bit low gain, we can choose 31 and 31 or 31 and 34 as the gains of our two stages. And again, we would need Vref going into each of these with a Vref generator. What's our gain bandwidth product now? Well, if we take the 1 megahertz, divide that by 31, we have 32.26 kilohertz. And if we take the gain of 34, we have 29.4 kilohertz. Okay. Now, if we take two stages like this and multiply the gains together, then you're going to get slightly lower corner frequencies because, particularly if these two things exactly matched, they would each have a corner frequency at, say, the 32 kilohertz. But then, if you have a gain of square root of 2 over 2, and then another gain of square root over 2, at the corner, what would have been the corner frequency for each amplifier separately, you'd only have a gain of a half at that. But because these two aren't happening at the same place, it's basically just the lower corner frequency here that's going to determine things. But that's a good deal more than our 20 kilohertz. So this looks fine in terms of gain bandwidth product. What about the problem with input offset? Well, we again had the high-pass filter here. So that got rid of the V bias. But the input offset on this amplifier is still plus or minus 4 millivolts. And we're still multiplying that by either a little less than or a little more than 1,000. So we're still getting a plus or minus 4 volt offset on the output. Haven't solved that problem. But here's an easy solution. What we can do is put in the high-pass filter, put in that gain of 31, put in another high-pass filter, put in that gain of 34, and now all these things hook up to the same Vref. And these can be, well, let's make this a little bit lower than 10 hertz. Maybe we can make this about 6 hertz this time. And that way we can be sure that the 10 hertz will still go through both of the filters without getting too much attenuation. All right, what is this doing? Well, we had a plus or minus 4 millivolt offset here, which got multiplied by this times 31 here. But that wasn't enough to cause this thing to clip. So it just gives us, what's 4 times 31? 124 millivolt offset here. It's actually a good idea to write all these things down, because one of the things about a block diagram, it's not enough just to tell what the blocks are. You have to say what the signals are. So this one was V bias plus or minus 1 millivolt AC. After the high pass filter, we have V ref plus or minus 1 millivolt AC. After the 31 times gain, we have V ref plus or minus 124 millivolts DC plus or minus 31 millivolts AC. After you run it through the high pass filter, the extra DC bias goes away when we just have V ref plus or minus 31 millivolts AC. And then when we multiply by 34, that's going to give us the Vref plus or minus 1.054 volts. And we're going to have some offset here. There was plus or minus 4 millivolts offset there, times 34 plus or minus 136 millivolts DC. So if this is good enough for us, we can say, all right, this is not going to be so much with the plus or minus 1 volt, 1.05 volt signal. The plus or minus 136 millivolts DC offset may not be a problem for us. May not cause any clipping. We would have to perhaps do a little calibration of this thing to figure out how much this DC offset was, if the input value here we really cared about DC on, but we were getting rid of the DC in the signals there, so this should be in many applications acceptable. What if it's not? What if we're saying we really do not want to have any, or as little as we can get away with, DC offset? Well, one possibility is to go to a stage where the final stage has a gain of 1. If you've got a gain of 1, then, and with the high pass filter in front of it, then the signal here is going to be Vref plus or minus whatever the signal is, and the output here will be Vref plus or minus the 4 millivolt offset plus or minus the signal. So I could have Vref plus pretty large offset here, plus or minus the signal. The high pass gets rid of this offset, and then the times 1, a unity gain buffer, which we'll get to in a little while, introduces only as much offset on the output as it has on the input. And in fact, if we're being very concerned about that offset, it's even possible to use a gain here less than 1. And if we use a gain less than 1, we can actually be reducing whatever the input offset is at the output, at the expense of reducing our overall gain. So there's a lot of different reasons why we might want to use multi-stage amplifiers. The ones that come up most often in this course are the desire to have sufficient bandwidth while using an amplifier that doesn't have a very high gain bandwidth product, and compensating for the input offset when we want to get a large gain. Because if you amplify that input offset without doing something to remove the offset at the intermediate stages, you can end up with your final DC offset being large enough that you clip or even lose your signal entirely. Okay. There are undoubtedly other reasons why someone might want to use multi-stage amplifiers, but these are the important ones for this course.